Continuing our description of ionic structure. So before that we ended with sodium chloride and cesium chloride cubic structures, ratio cation coordination numbers in sodium chloride was 6 octahedral and 8 for cesium chloride cubic. Now there is one-to-one structure with smaller coordination number 4, which is zinc sulfide. Name is sphalerite, it's mineral coming from spharelos, treacherous. Another historical name is zinc blende. Blend, Old English and in German means mistake. So addition of zinc sulfide by medieval, not ancient, metallurgist resulted in wrong outcome, wrong melt. So these additions were named blends. There are plenty of such minerals that historically have named blends. So that's why zinc blend structure. Anyway, what is the structure about? It's cubic. You can see coordination number of zinc is 4. Zinc is much smaller than sulfur, and coordination number of sulfur is 4 as well. It can be represented in such a fashion. Alternatively, if we look at it as a cubic structure, there are 2 cubes, zinc cube and sulfur cube, with face center structure, and it's shifted a little, making inclusion of 2 of them. A similar shift was in cesium chloride and in sodium chloride, just by different distance and different direction. Zinc blende is not the only zinc sulfide structure. There is another zinc sulfide, also with coordination number 4, which is wurtzit. It's different mineral. It's visible that here it's hexagonal. It's interesting, it somehow resembles picture with diamond. This structure is exactly like diamond if you put carbons on top of each of these atoms. This will be, if you'll take only one of this, it will sort of atom, it will resemble graphite. Another interesting structure is ratio 1 to 2, fluoride, calcium fluoride. It's colorless mineral, but because of impurities, it's often beautifully colored. Structure is again cubic, with twice more fluorine atoms than calcium atoms. There are plenty of other compounds with similar composition. Element 1, 2 atoms of element 2, that will have this fluoride structure. If you'll have 2 different cations, we often have perovskite structure. Original perovskite was calcium titanium oxide or calcium tannate. It has 2 cations. One of them is very small relatively, with charge +4. Another is much larger with charge +2. Coordination number of +4 is 6. It's octahedral. Coordination number of +2 calcium is 12. And now there are 3 oxide anions. This is very interesting motif that again you can find in plenty of different structures. It can be any element with +2, anything with +4. Alternatively, you can have +1, +2, and -1 cation. This is perovskite structure of lead iodide with bulky organic cation. Such perovskite compounds are very promising possibility for solar cells. So again, they have the same perovskite structure, but chemistry is absolutely different. One more compound containing 2 different elements of composition of AB2X4 is spinel. Best representative is magnesium, aluminum, O4. So here is 1 ion 2 plus, 2 ions 3 plus, and 4 ions -2 oxide. We have tetrahedral environment for 3 plus, which is aluminum in this case, and octahedral environment for magnesium. Pineal itself is colorless, but because of impurities it can give fantastically beautiful coloring crystals from black to red to different hues. It's a gemstone. Crown of the United Kingdom is adorned by black Prince ruby, which is not ruby but pineal. Iranian crown jewels contain so-called Samarian pineal that by legend was owned by Moses when he led Jews out of Egypt. One more detail about crystalline compounds. All the compounds we were talking about had ideal structures, so all atoms were placed in proper position. In reality, many of real crystals, if not all, have some defects. Let's look at some most common defects. One is Schottky defect, when you have 1 anion lost and 1 cation lost. So 2 atoms lost in a structure, otherwise everything is full. Another option is Frenkel defect, when one of ions is misplaced from its original position. So you have overall composition still correct, but otherwise you have some deficiency in periodicity of the structure. One more possibility is when you have ideal structure. This is ideal iron oxide structure, Fe2 plus O2 minus, but one of iron ions was oxidized. As a result, Fe3 plus is smaller and it prefers tetrahedral coordination with coordination number 4. As a result, of course, you need less number of iron ions to balance the charge because you have 3 plus. So you have vacancies. Some of positions that should be occupied by iron are simply empty. Another option is that instead of an ion, you simply have a trapped electron that is sitting on orbital somewhere between, located, and there is no nucleus inside. That again gives you some defects. Such defects can provide coloring for otherwise colorless crystals. They can change their electronic properties. It's fantastically interesting physics.